Hi, buddy. How's it going? Today we're talking about exponential functions. Exponential functions are the third major function that we study in Algebra 1. Okay? First we talked about linear functions and then quadratic functions and now exponential functions. Exponential functions are written in the form of y equals a times b to the x power. Because the x is up here, that's what makes it an exponential function. The x is not the base of the exponent, it is the exponent. Okay? There are a couple of rules that we want to follow for this. Okay, first of all, the a is going to be our y-intercept. So we always want to make sure that a is greater than 0. Okay? We don't want to have a y-intercept in the negatives, at least not for Algebra 1. Okay? As we get into higher maths and we start looking at transformations, then you might have a negative a value. You might have it flipping and turning and stuff. We're not worrying about that right now in Algebra 1. In Algebra 1, a has to be greater than 0. Okay? Then the next thing is our b. Our b is what gets multiplied each time. So if we're multiplying by 2 or by 3, then we're going to multiply by 2 every time we plug a number in. Okay? Or every time we move to the next x value. There are a couple of rules for b. The first rule is that if it is between 0 and 1, then it is a decay. It's an exponential decay function. Means it's getting smaller. And if it is greater than 1, then it is an exponential growth, meaning it's getting bigger. Okay? Now the thing about exponential functions, these get to really big numbers really, really fast, or really small numbers really, really fast. Okay? And there's something called an asymptote. Now, an asymptote, for every exponential function, there is a line that it's never going to quite reach. Okay? And so that line is called the asymptote. The line that exponential function never quite touches. It looks like the graph kind of flattens out at a certain point, and you'll see that here with some graph examples that we have in just a moment. So where it starts kind of flattening out, it's not that it's actually like staying on one specific value the whole time. What's actually happening is that the value of y is getting smaller and smaller and smaller. So it's getting closer and closer and closer to that line, but it's never actually going to touch it. Okay, that's an asymptote. I did want to kind of give you a couple of examples of some common exponential functions that we know about. One that's current in our news now as I record this on April 17th of 2020 is disease spread. Okay? If you have some disease that one person has a disease and they are able to spread it to 2 people. Well, each of those 2 people will spread it to 2 people. And each of those 4 will spread it to 2 more people. Okay? And then each of those 8 people will spread it to 2 more. Okay? This is an example of exponential growth. And what's happening is that every generation of spread, the number of people that have this disease doubles. It goes from 1 to 2 to 4 to 8 to 16. And if we keep going, the next generation will have 32 and then 64 and then 128. And it'll keep getting larger and larger from there. Now, this is an example of exponential growth. Okay? An example of exponential decay would be March Madness. Okay? That basketball season in March where we start out in round 1 with 64 teams. And then at the end of round 1, half of those teams have been knocked out. So now with round 2, we have 32 teams. And at the end of round 2, half of those teams have been knocked out. So round 3 has the Sweet 16. So 16 teams that are battling to get to the top. Round 4 is the Elite 8. So it's top 8 teams. Okay, and each time half the teams are being knocked out. And as we go to round 5, now we're in the final 4 there. See how quickly we went in 5 rounds. We went from 64 teams to now we're 4 teams. Round 6 is the championship. And the winner of round 6 is the NCAA champion for the year. Okay, that's an example of exponential decay. All right, so we're going to look at a couple of, we're going to look at an example of growth and an example of decay. I've kind of given you some examples that you might relate to or you might have heard of before. But let's look at it in table and graph format. Now this first one is our growth, okay? As you can see, this is a growth. And I know it's growth because as my x values are getting larger, then my y values are getting larger as well, okay? The first thing I want to do is I want to look for my y-intercept. On my table over here, I see my y-intercept is at 0, 1. That 1 is my a value. Now to find my b value, I go for my y-intercept and I just go over 1. So if I go over to 1, okay, starting out here at 0, 1, if I go to where x is 1, my y value is 2, okay? Now really I'm taking the 2 y values. I'm taking the 2 and the 1. I'm going to divide. 2 divided by 1 is going to give me 2. On my table, if I look on my table to get from 1 to 2, I had to double that. I had to multiply by 2. To get from 2 to 4, I had to multiply by 2. So as we're going larger, as our x values are getting larger, so are our y values. They keep multiplying by 2 each time. And if I look where my x's are negative, it's even happening there. So this 0.25, if I multiply that by 2, I get 0.5. If I multiply 0.5 by 2, I get 1. Okay? So that pattern of having to multiply by 2 even extends when we have negative x's, negative x values. This 2 is my b value. So when I do my equation, my y equals a to the b, a times b to the x power, I'm going to substitute in a 1 for my a, a 2 for my b, and it's to the x power. So there's my equation for it. Now there is one more thing that we kind of start to see the beginnings of it here, but we're going to see even more on the next graph. So let me pull this over here. And you kind of see it on the table that these y values are getting smaller and smaller and smaller. They're getting to be longer and longer decimal values, okay? So what ends up happening, and this first graph is just a small section of this bigger graph, okay? So this first graph is just about this much of the larger graph. Okay, so you're really not seeing a whole lot. But if you look at the larger graph where we expanded it out and looked at larger values, okay, as we keep multiplying by 2, we get really big really fast, okay? At when x is 8, our y value is over 250. It's 256. At 10, if we were to keep going up to where it's 1 times 2 to the 10th power, that's going to be over 1,000. Okay, it's going to be 1,024. Okay, my y-intercept is way down here at 0, 1. And here's 2, 4. Okay, so what you're seeing here at this point, let me highlight this, is that this section of the graph, this section of the function, is getting closer and closer and closer to our y-axis. Now it looks like it's sitting on it, but that's because of the scaling of this graph, okay? There's something here called an asymptote. That asymptote is a line where it's never going to cross, okay? We talked about that a minute ago. The asymptote for this function is at y equals 0. For algebra 1, the asymptotes for all of our exponential functions at this level is going to be y equals 0, okay? Because we're not moving it off of that axis point, okay? When you get into algebra 2, your asymptote may change based on what transformations you apply to the function, okay? So we said our equation equals 1 times 2 to the x power. Our asymptote is on the x-axis, okay? And the equation for the x-axis is y equals 0, okay? So that's always going to be our asymptote, no matter what the equation is, okay? At least for algebra 1. Once you get into algebra 2, that asymptote will change. Okay, we're just looking at basics, the starter part of exponential functions. Let's look at what happens for an exponential decay. Okay. Here, if we look for our y-intercept, again, our y-intercept is at 0, 1. And so our a is still going to be 1. Okay. This time, if I go from 1 to 1/2, well, I multiplied by 1/2. If I go from 1/2 to 0.25, a quarter, again, I multiplied by 1/2. And from 0.25 to 0.125, I multiplied by 1/2. Okay. If I come in from the other direction, I could see that to go from -1 to 0, I went from 2 to 1. So again, I multiplied 2 times 1/2 to get 1. I multiplied 4 times 1/2 to get 2. And 8 times 1/2 to get 4. Okay? Okay, I apologize for alarms going off. All right, so here is my y-intercept at 0, 1. And if I go back, because it is decay, it's going down and my y values are getting smaller while my x values are getting larger. Okay, so if I go over to 1, then this point is at 1 and 0.5. If I go up, I go over to -1, then I'm at -1, 2. Okay, so I can still see that if I take that -0.5, or sorry, that positive 0.5 divided by 1, my b value is going to be 0.5. So here's my b value. Okay, so my equation, when I fill in my equation, y equals 1 times 0.5 to the x power. Okay, you could write it as 1 times 1/2 to the x power. And here I'm going to use parentheses instead of a decimal value because the whole 1/2 is to the x power. Okay, I still have my asymptote, and I'm going to come over to the larger graph. Okay, here's the larger version of that graph, and you can see that asymptote right here, where that line is getting really, really close to the x-axis, but it's not actually touching it. And again, if you look at the scaling here, we're counting by 100 on the y-axis, so it really does look like it's sitting on the x-axis, but it's not. It's just getting really, really close. So our asymptote, again, is at y equals 0. Okay? So our equation we had was y equals 1 times 1/2 to the x power with an asymptote at y equals 0. Okay? Those are your exponential functions. And that's what we're looking at this week. We're just looking at those key features. Find the a, find what is your y-intercept, and then find your b. What is it multiplying by each time? That's all you need to be able to write these functions. Okay? And all right, guys, I'm going to leave it there for today, and I will talk to y'all later. Bye.